All right, as I was walking around, like I saw some people like instead of saying things like I did, which was kind of basic, that the graph bounces at 2, someone was saying there's a relative minimum at 2. That's great. And then like another one where I just said it bends, someone was saying point of inflection. So you guys, some of you are being a little more mathematical, using more mathematical terminology than I did. But either way, it's fine. So number 1, I filled out a while ago. Let's look at number 2. So the x-intercepts here are going to be 2 and 4. -4, I should say. What did you guys say about the degree? It's also 4. Good. And then, so what was happening at x equals 2? What was this behavior on the x-axis? It does go through. Does it go straight through or does it do a little wiggle? Do y'all remember? It wiggled. So let's call it bends. So it bends at x equals 2. Or you could, this one is actually a point of inflection and changes from concave down to concave up at that point, but bends is fine. That's all I need you guys to say today. And then what about a -4?
It starts to become more concave, but it goes straight through.
Straight through, good. All right. And then this last one, there were only 2 x-intercepts. But what would the degree be? 4. And I don't remember, someone just asked me a second ago, the degree should match the number of solutions, not always match the number of x-intercepts. I know that seems weird, but that equation, if we set that this function equal to 0, the number of solutions should match up with the degree. So there should be 4. But there were only 2 x-intercepts. So what's going on there? They're imaginary. So only real zeros are x-intercepts. These polynomial functions can also have imaginary zeros, and they do not show up on the x-axis, or they don't show up on the graph at all. And so we had you take this part of this function and set it equal to 0 and solve. So what would you guys do first to solve? Good. And then what? Take the square root. And every time you solve an equation by taking the square root, you have to do the positive and negative square root. And what is the square root of -4? 2i. So anytime you take the square root of a negative, you get an imaginary solution. So you just put an I there and just think of it like a positive 4, and it's going to be positive and negative 2i. All right, so can a quadratic equation ever have one real and one imaginary solution? No. So imaginary solutions always come in pairs because you get them because you take the square root of a negative. And when you take the solve by taking the square root, you have to do the positive and negative. So let me write that down with less words. So we're going to say no because, whoops. Imaginary solutions come from taking the square root of a negative. And solutions are always plus and minus. So you guys are going to hear me say, when you solve by taking the square root, you have to take a positive and negative square root. I'm going to say that so many times, but some of you are still not going to do it. Like I had my son in class for 3 years, and he still sometimes in calculus forgot to do the plus or minus. So I'm going to say it. Hopefully you'll always do it, but there's a good chance some of you are going to forget your plus or minus, but try not to. All right, so let's fill in the notes on the back. Some of this I'm hoping that you remember from Algebra 2, but a zero of a polynomial function is an x value that makes the function equal to, what do you guys think? Zero. All right, and real zeros are always going to be the x-intercepts on the graph. All right, so I kind of use imaginary and complex as the same thing. They're slightly different, but imaginary zeros or complex zeros don't appear on the graph. The graph is only real numbers. And another thing you need to know about imaginary and complex zeros is one of the last things we talked about on the other side is they always come in conjugate pairs. Now, when I was figuring all this stuff out yesterday afternoon, I texted the two honors algebra 2 teachers and asked them if you guys knew what conjugate pairs were, and they said no. So I'm going to give you like a quick lesson on complex conjugates. It's super simple. I don't even know why we don't do it in algebra 2 anymore, but it's fine. But an imaginary number is like the number 2i. And the conjugate of 2i is going to be negative 2i. They are conjugates. Now, the awesome thing about conjugates is when you multiply them, you don't get an imaginary number anymore. Now, a complex number is a number like 3 plus 4i. It has a real part, which is 3, and an imaginary part, which is 4i. And the conjugate is not just the opposite. The conjugate is not negative 3 minus 4i. So conjugates have the same real part and opposite imaginary parts. Now, I have a feeling this is going to come up again, and I'll give you a better lesson on conjugates, but for what you need to know for today, if 2i is the solution, then negative 2i also has to be. If 3 plus 4i is a solution, 3 minus 4i has to be a solution. They come together. All right, the main goal, I think, of this lesson is multiplicity. And last year was the first year you learned about multiplicity, and it probably was kind of confusing. This year, it's going to seem easier because you have that background knowledge. But multiplicity is simply the number of times a factor occurs. So you guys can stay on this side. I'm going to scroll up to what we just did on the other side. So if we go back to this one, this 0, which was 2, because the factor occurred twice, had a multiplicity of 2. This 0 here, that was also 2, occurred 3 times, so it had a multiplicity of 3. And whenever the multiplicity is 3, this is what's going to happen. Whenever the multiplicity is 2, where is it? This is what's going to happen. So we're going to write all that stuff on the other side too. All right, so I have just this generic function. In this function, the 0 is going to be p. And we would say p has a multiplicity of, what do you guys think? What would the multiplicity be? K. So K is the multiplicity. So on this table we're about to fill in, every time it talks about K, it's talking about multiplicity. All right, so if K is odd, it's definitely going to cross over the x-axis at that point, or at the 0, but it can do different things as it crosses. So I'm going to draw one. It's just going to go like that. So if it just goes straight through, just passes straight through, then the multiplicity is 1. We're going to say k is 1. We're just going to say passes straight. Oops. I definitely did not give myself enough room. All right, now I'm going to draw one. It still crosses, but as it crosses, it bends. And that's whenever there's going to be a multiplicity of 3. So these are definitely the odd multiplicity. We're definitely crossing the x-axis. All right, and then even multiplicity is whenever you'll have like a little relative max or relative min just sitting on the x-axis. And I call that bounces. That's not a super mathematical term. So anytime the multiplicity is even, it's just gonna bounce. Now, I was looking through the standards for today, and there's a bunch. There's like 7 standards we're covering today. I just want to write some terminology that the AP people wrote, and you might not understand it right now, but eventually you probably will. So where it just bounces, the way they worded it is that it's tangent to the x-axis. And in geometry, you might have learned what it means for 2 things to be tangent, not like sine, cosine, and tangent. That's not the tangent I'm talking about. So when things are tangent, they just barely brush up against each other. So they just touch each other and then go the other way. That's what's happening on the even multiplicity. All right. A couple more things. So a polynomial of degree n has exactly n zeros, and we were talking about that on the other side. That's if you're including the multiplicity. So if a 0 has a multiplicity of 3, you actually count it as 3 zeros. And can be written in factored form or intercept form. I tend to call it factored form instead. And then those zeros are real and imaginary zeros. All right, so let's look at some examples. So knowing everything we know from Algebra 2 and from this year, we can look at a graph and tell the zeros and each of their multiplicities. So let's just start on the left. What's the first 0 that you guys see? -3. And then looking at its behavior, like what it does at the x-axis, what would you say its multiplicity is? 2. So if it's tangent to it, or there's a relative minimum or relative maximum, or if it bounces, all of those mean the same thing, then the multiplicity is 2. All right, what's the next 0 you guys see? Then what's the next x-intercept? 2, good. All right, and then looking at its behavior, what would you say the multiplicity is? Does it bend or does it go straight through? It bends, so it's 3, good. All right, and then we have one more at 4. What do you guys think about the multiplicity? 1. Straight through was 1. Nice job. Okay, and then B asks, does g of x equals 0 have any imaginary solutions? What do y'all think? How many totals should there be for this? There should be 6. So if we count up all the multiplicities, what do you get? 6. So is there any way there's any imaginary? No. 6 is what we have. So we're going to say the answer to the question is no. Because adding the multiplicities equals the degree. So that means all the zeros are real zeros. Okay. And then for C, we're going to write the equation, and we're just going to write it in intercept form. We aren't worrying about multiplying out. That's unnecessary work for us at this moment. So let's just start with the purple one. We have x is -3. So what factor would give you that 0 of -3? X plus 3. Very good. My last class didn't understand what I meant when I said factor, but it sounds like you guys did. All right, and then if it has a multiplicity of 2, what do I need to do? Have a power of 2. Is that what you did? Okay, you went to the next question. So if the multiplicity is 2, that should be that power. All right, and then the next factor is x minus 2. And what power should I use on this one?
3.
3, good. All right, and then finally I have x minus 4 for 4. Do I need to have a power for multiplicity of 1? That's it. All right, any question? It's not too terrible. All right, let's do a couple more. So on number 2, this time we don't have a graph, but we know some zeros. We know 4 has a multiplicity of 2. We know -2 is a 0. It doesn't really say anything about multiplicity. And it says 3i is a 0. So if 3i is a 0, what else is a 0? -3i. So they will trick you. See if you're not paying attention and you just count the zeros they give you. But if there's an imaginary 0, conjugate is also a 0. So what is the minimum degree of this polynomial? 5. Good. So we count, this is 2, and then 3, 4, 5. Yep. All right, and then we're going to write the factored form. This one is not called anything, so we'll just call it f of x. All right, and then so for a 0 of 4, we're going to do x minus 4, and then it's squared because the multiplicity of 2. For -2, we'll just do x plus 1. And then it's going to look weird, but it's fine. For 3i, we're just going to do x minus 3i. And -3i, we're going to do x plus 3i. All right. What questions do you guys have about that? All right. So this is the last one. I went ahead and graphed it just to save on time. There it is. All right. And looking at the factored form or the intercept form, we knew 6 was going to be a 0, but the other one isn't a linear factor, so we didn't really know what was going on there on the graph. So how many zeros should this one have? What would the degree be?
Oh.
The degree?
Oh, no.
It's okay. The degree is 3. So there is only one real 0 from the graph. So that means the other 2 are going to be imaginary. But we can just go ahead and say x equals -6 is a 0. The other 2 are going to be a little bit more work. Okay, so on the other side, we had one that we solved, and we just solved it by subtracting and taking the square root. Am I going to be able to do that on x squared plus 2x equals plus 5? No. So there's 2 things we can do. We can do the quadratic formula, or we can do completing the square. Last class, I did it both ways, and we all agreed quadratic formula, just based on where we are this year, that's probably the one you're going to feel the most comfortable with, but you need to remember it. Anybody remember it? Wow, that's impressive. Did you learn a song? You just remember it? There is a song. I don't sing in front of people, so sorry. I might play it for you one day. There's definitely a song. So in this situation, A is 1, B is 2, and C is 5. So I'm just going to fill all that stuff in. Now when I do the quadratic formula, I go ahead and square B as I write it down, so try not, hopefully that won't confuse you. So instead of writing 2 squared, I just went ahead and wrote 4. You can do whatever you want to do. We cannot put this in the calculator all at one time, but we can do 4 minus 4 times 1 times 5. And we're going to get the square root of negative 16. And hopefully it didn't surprise you that you got a negative under the square root, because we already knew those were going to be imaginary solutions. All right, so what is the square root of negative 16? 4i. And then try your best to remember that when you're doing the quadratic formula, you wait to the very end to reduce it. I always draw this heart. And if everything inside the heart can be reduced by the same number, then do it. If it won't, then you can't. And always wait to the end. And so everything inside the heart can reduce by 2. And those are the other two solutions, negative 1 plus 2i and negative 1 minus 2i.
Where'd you get negative 1?
Negative 2 divided by 2. So inside the heart, I reduced everything by 2. Right, any other questions? Okay, one more. The last thing we're going to do is rewrite this in factored form or in intercept form, however you want to word it. We already know one factor is x plus 6, so that's easy. All right, and then remember, when we do this factors, you're just doing the opposite. It's weird on the other one, so we're just going to do minus, and then in parentheses, we'll do negative 1 plus 2i, and then x minus negative 1 minus 2i. And I'm fine with you leaving it that way. If you wanted to distribute the negative, it's not wrong. It's just more places for you to make a mistake. All right, do you guys all understand where those factors came from? You good, Torin?
Yeah.
Okay. All right. Let me give you a worksheet.